Good morning. Today we're going to talk about some application problems for the last 4 sections that we have talked about in exponential and logarithmic functions. So when we look at these problems are precisely going to talk about the exponential growth, decay, or the logistic growth and decay formulas. So if I look at my first problem, it talks about Q equal to Q naught e to the power minus kt, and it is asking me to solve for the constant k. This formula is widely used in chemistry. So what I do, I divide both sides of this equation by Q naught. Remember, my intention is to get the exponential term by itself. So I get Q divided by Q naught equal to e to the power minus kt. Since it is an exponential with base e, I would like to take natural log on both sides and call it natural log of Q over Q naught equal to natural log of e to the power minus kt. This being an exponential function of base e and this being a natural log function of base e, they cancel each other and you get minus kt. Since I'm solving for k, I will divide both sides by minus t, and if I do so, I will isolate k. So what I get k is equal to natural log of q over q naught over negative t. In general, an equation of this format is called a growth or a decay equation, where q is called the final quantity, q naught is called the initial quantity, k is called the rate of growth or decay, and t is called the time. So let's try to remind ourselves about the interest problems that we were talking about when we defined exponential function for the first time. Example 2 is a similar problem. Suppose that $12,000 is invested in a bond fund and the account grows to $14,309.26 in 4 years. And I want to understand what is the rate of interest. Assuming this interest is continuously compoundified, I will say the final amount is $14,309.26 after 4 years. Remember, your initial investment is $12,000, and if you recall the continuous compoundification formula, it says final amount equal to principal invested times P times e to the power the rate of interest times the time of investment. And I want to know what will be the rate of interest. So this is your principal invested, $12,000, and you know that time is 4 years and you want to find how much is R. So this is basically an exponential equation which you want to solve. So why don't we go ahead and divide both sides by 12,000, our usual way of solving exponential equation. So then I will use our base e to take natural log on both sides. So I will get natural log of $14,309.26 over $12,000 is equal to natural log of e to the power 4r. As usual, I will say natural log of $14,309.26 over 12,000 is equal to 4r, because e and natural log cancel each other. Remember, you are solving for r, so you will divide both sides by 4. So the rate of interest is almost found out. It is natural log of 14309.26 over 12,000 and all over 4. What I will do now, I will calculate this number in our calculator, and then I have to answer this question in terms of percentages because this is talking about the rate of interest. So let's go to our calculator. And we are going to type in these numbers. So it is 14,309.26. And I'm dividing it by 12,000. So this is the number I'm going to get. And I will take the natural log of this number. So I'll say natural log of the answer. And that's going to be this number. And remember, I'm going to divide this entire quantity by 4. And then I'm going to multiply this thing by 100. 100. So my R is found out. If I round it to 4 decimal places, I get 0.044. So that's your R is equal to 0.044, but I'm going to change it to percentages. So multiply by 100. So rate of interest, which I wanted to find out, is going to be 4.4%, and that will answer the question. So the things that I want you to remember, pretty much all the application problems are going to be relating somehow with these type of formula. In this problem, I have assumed two things. I have assumed that I want to know what is the rate of interest that I did not tell you initially. And I have also assumed that compoundification is continuous. Compoundification of the money is continuous. So let's try to see other types of exponential application problems. Population problems are one of the more famous problems that we can see where we are going to use the exponential growth rates. The population of two countries are given for January 1, 2000 and January 1, 2010. Write a function of the form pt equal to p0 e to the power kt to model each population pt in millions. T is years after January 1, 2000. So it is about Australia and Taiwan. The population in millions are given in 2000 and 2010. And the first question is asking me, find the population model for either countries. So let's try to answer this question. First one, let's do it for Australia. And again, you know the population model. PT is the final population. So let's do it in 2010. 2010, the final population for Australia is 22.6. And the initial population in 2000 is 19. That's your P naught, the initial population. It's 19 million times e to the power k t. Well, what is t in 2010? So in 2010, t will be equal to 2010. It's the year after 2000. So that is 10. So I'm going to use 10 for t. And see, that's exponential equation which we're going to solve to know the k, the growth rate. So divide both sides by 19 first. And I get 22.6 over 19 is equal to e to the power 10k, because the base is e. Like other problems, we're going to take the natural log base 10. So I get natural log 22.6 over 19 equal to natural log of e to the power 10k. So natural log of 22.6 over 19 is equal to 10k. You divide both sides by 10, and that talks about the growth rate of Australia, which is natural log of 22.6 over 10 all over 19 all over 10. So let's find this number. And if I did not tell you how many decimal places you're going to round your answers, always round to 4 decimal places. So natural log, so first do 22.6 and then divide it by 19. And then I do natural log of the answer. And then once I have found it out, I will divide it by 10, round to 4 decimal places. So I'll get 0.0174. So K for Australia is 0.0174. Remember, this question asked you to write the population model. So you're going to say P of T is equal to P naught. Now P naught is the initial population, which I know for Australia it was 19 million. So 19 times e to the power 0.0174 t. And that is called the population model. As I change time, it is going to give me the population in a certain year after 2000. So I will repeat the same work just for ourselves to remember. I will say PT is the final population, so that in future we can refer back to these things. P naught is the initial population. Most of the time in the problems, you will be given with the initial population. If not, you put t equal to 0 and find the value of P naught. So I will also write it down for you to refer back to it. T equal to 0 will give you the initial population most of the time, unless otherwise mentioned. So let's do it for Taiwan now. T does not change. So when I'm working with Taiwan, T is still 10 because we are talking about 2010. Final population, whereas, is 22.9. I'm sorry, is 23.7 for Taiwan. Initial population is also different, it's 22.9, and it is going to be e to the power, I do not know the k, t I know, it's 10. Repeat the same process, you divide both sides by 22.9. So you get 23.7 over 22.9 equal to e to the power 10k. Then you take natural log on both sides because the base is e in this problem. So natural log of 23.7 over 22.9 is equal to natural log of e to the power 10k. Of course, I get natural log of 23.7 over 22.9 is equal to 10k. Divide both sides by 10 to isolate k. And I get k is equal to natural log of 23.7 over 22.9 all over 10. So I'm going to simplify this in my calculator. Again, remember I'm rounding my answers to 4 decimal places. So I will first do 23.7 and I will divide it by 22.9 and then take the natural log of this answer, and then I will divide this answer by 10, which will give me the k when rounded to 4 decimal places. So that's 0.0034. So I'm going to go ahead and say that this is approximately equal to 0.0034. I am interested in the population model for Taiwan, and I'm going to say that the population model for Taiwan will be P of T equal to the initial population, which is 22.9 times e to the power k, which is 0.0034 t. And now I have answered part A of the question completely. Part B is asking me, use the models from part A to predict the population in January 1, 2020 for each country. Round your answer to the nearest whole number. Okay. So we are going to use the population model for either country. So first, for Australia. We found this model. For Australia, we will say model is P of T is equal to 19, and then I have e to the power 0.0174 t. For Taiwan, I have a different model, but I do have a model, and that's P of T is equal to 22.9 times e to the power 0.0034 times t. Let me check it one more time if I have remembered it right. It is 0.0034 t. What's next? In 2020, I want to know the population. So in 2020, t is going to be 2020 minus 2000. So t this time is 20 for either situation. So put t equal to 20 and that will be your answer. Except you have to round it to the nearest whole number. So 19 times e to the power 0.0174 times 20 for Australia. And for Taiwan, you will get P of 20 equal to 22.9 times e to the power 0.0034 times 20. So let's find these two numbers in our calculator one more time. So we have 0 for Australia. I'm going to do 0.0174 times 20. And then I'm going to raise it to the power e, so I will say that e to the power, the answer, and then I'm going to multiply it by 19, that's the initial population, so times 19, and round it to the nearest whole number, which is 27. So it is approximately 27 million people. The population in 2020, January 1st, the population of Australia is around 27 million. How about Taiwan? So it's similar work. We're going to find it out in our calculator and round to the nearest whole number. So I have 0.0034 that I multiply with 20, and the answer is 0.068. Then I say e to the power, the answer, and I multiply this quantity by 22.9, which is the initial population. So the population of Taiwan, rounded to the nearest whole number, is 25 million. So for Taiwan, I get around 25 million in the beginning of 2020. That answers the prediction, the estimation for part B in this problem. Part C is asking you, Australia had fewer people than Taiwan in 2000. That's true, because Australia had 19 million people and Taiwan had 22.9 million people. Yet, from the result of part B, Australia will have more people in 2020. Why? The result indeed says so. Australia will have 27 million and Taiwan will have 25 million. Why this is true? So I will say that Australia will have greater population as the growth rate for Australia is higher. So if you compare the two growth rates, Australia's growth rate was 0.0174, which is almost 1.74%, whereas Taiwan's growth rate is 0.0034, which is 0.3%. Okay, so we're going to answer the last question in the last part of this question. Use the models from part A to predict the year during which each population will reach 30 million people if this trend continues. So now for part D, I am trying to understand when the final population will be 30. So for Australia, I will say 30 equal to 19 times e to the power 0.0174, and I want to know the t. What will be the time? So let's see. Divide 19. Again, exponential equation. So divide both sides by 19. You get 30 over 19 equal to e to the power 0.0174t. So then you take natural log on both sides. You get natural log of 30 over 19 equal to natural log of e to the power 0.0174t. So natural log of 30 over 19 all over. And in fact, I can do one more step if you don't understand why I said all over. So I will go ahead and say natural log of 30 over 19. Remember, these cancel, so you get 0.0174t. Divide both sides by 0.0174. And that will tell you t. So let's calculate that. Divide by 19, and I'm going to take the natural log of the answer. Finally, I will divide it by the growth rate 0.0174. So it's around 26 years from 2000. So I will say that t is rounded to a whole number is around 26 years. So hence in around from 2026 years will give you 2026. So around 2026 it is going to be 30 million. How about Taiwan? So again do the same thing. You said 30 equal to 22.9 e to the power 0.0034 t. You are interested in finding t for Taiwan's population. Pretty similar work. Divide both sides by 22.9. So I get 30 over 22.9 equal to e to the power 0.0034 t. Take natural log on both sides. So I get natural log of 30 over 22.9 is equal to natural log of e to the power 0.0034t. Again, this cancels, so I get natural log of 30 over 22.9 equal to 0.0034t. Divide both sides by 0.0034 and then simplify that number in calculator. This has isolated t, so I will go ahead and say that once I have done it, I'm going to say that t is going to be approximately equal to, so let's do this work. I will do 30 over 22.9 first. And then take the natural log of this answer. And finally, I divide it by the rate of growth, which is 0.0034, round to the nearest whole number. So I'm just going to say 79 years. See the difference? So 79 years approximately from the year 2000. So I will say it will be 50 million in Taiwan in around 2079. Answers my question. Let's carry on to page number 3 and see what problems we have there. The isotope of plutonium-230 Pu is used to make thermoelectric power sources for spacecraft. Suppose that a space probe is launched in 2012 with 2 kilograms of plutonium-238. If the half-life of plutonium-238 is 87.7 years, write a function of the form Qt equal to Q naught times e to the power negative kt to model the quantity Qt of plutonium-238 left after t years. So first, we need to understand what we mean by half-life. So if Q naught is the initial amount, and if capital T is the half-life, then after capital T, amount left is half of the initial amount, which is Q naught over 2. Let's use these two information along with the decay equation. So see the final amount left, Qt, I'm going to call it half of the initial amount, which is equal to the initial amount times e to the power minus k, capital T, because I'm saying t is the time it has taken to reduce to half. What you can do? You can divide as usual both sides by Q naught. What will happen? You will get 1/2 on the left hand side equal to e to the power minus kt. And remember what I'm interested in. I'm interested in solving it for t. So I will say, let's take natural log on both sides. So natural log of 1/2 is equal to natural log of e to the power minus kt, which means minus kt, remember they cancel, is equal to natural log of 1/2. So what is the half-life? Capital T is natural log of 1/2 over negative k. In our problem, we know the half-life. What is the half-life? The plutonium-238 has the half-life of 87.7 years. So I'm going to go ahead and say that 87.7 years is equal to natural log of 1/2 over negative k. See, that helps you solve for k, and hence you will be able to write down the decay equation. How does that help me solve for k? Well, why don't we multiply k on both sides? That will help us get rid of this denominator. So I get 87.7k equal to negative natural log of 1/2, means k is equal to negative natural log of 1/2 over 87.7. That could be evaluated in the calculator, and then we will round it to 4 decimal places. So let's do that. I will do 1 divided by 2, take the natural log of my answer, and then I'm going to multiply negative with this thing, and finally I'm going to divide it by 87.7. So divide by 87.7, round to 4 decimal places, and I will get 0.0079, and that's the decay rate. So is equal to 0.0079. So how to answer the first question? It asks you to model it. So you will say Q of t is equal to Q naught e to the power negative 0.0079 t. Now remember, this one actually told you how much is the initial amount. It was launched with 2 kilograms of plutonium-238. So I can better this. I can say that QT, Q naught is the initial amount, which is 2 times e to the power negative 0.0079 t. Answers my first question. The second question is asking me if 1.6 kg of plutonium-238 is required to power the spacecraft's data transmitter, for how long the space probe will be active. So if the amount of plutonium-238 left is less than 1.6 kilogram, the space probe will not be active. So let's find out by what time the amount of plutonium-238 left will be 1.6 kg. So that is the final amount. I will use the model found in part A, use the final amount as 1.6 equal to 2 times e to the power negative 0.0079 t, and solve for the value of t. So first thing first, we divide both sides by 2 as usual. I get 1.6 over 2 equal to e to the power negative 0.0079 t. Then I take natural log on both sides. So natural log of 1.6 over 2 is equal to natural log of e to the power negative 0.0079 t. As usual, they cancel. You get natural log of 1.6 over 2 equal to negative 0.0079 t. Divide both sides by negative 0.0079, and that will give you an approximate value of t. And what I will do, I will round t to the nearest whole number, because it is talking about number of years, and I have not been given with any particular instruction how I want to round. So let's just round it to the nearest whole number. So I do 1.6 divided by 2, and I take the natural log of this answer. Then I divide it by 0.0079. But remember, I was dividing it by, so why don't I change it? Dividing it by negative 0.0079, which rounded to the nearest whole number will be 28. So the space probe will work for almost 28 years. After 28 years, the amount of plutonium-238 will be less than 1.6. So the thermotransplant is not going to work anymore. So my answer will be for about 28 years. For about 28 years, it will be active. Answers my question. So since it started in 2012, you can say like around 2040. The next type of equation that we will deal with are logistic equation. So let's try to understand these type of equations as well. So what I have is the population of United States, PT, in millions since January 1, 1900 can be approximated by PT equal to 725 over 1 plus 8.295 times e to the power negative 0.0165 t, where t is the number of years since January 1, 1900. The question that it is going to follow is evaluate P0 and interpret its meaning in the context of this problem. So think about PT. PT is given by this function 725 over 1 plus 8.295. So let me write down that much. 725 over 1 plus 8.295 e to the power negative 0.0165 t. What if I put t equal to 0? That's the P0, that what I'm going to try to find out. So it's 725 over 1 plus 8.295 e to the power negative 0.0165 times 0. Remember, this portion is just 0 after the multiplication. So I get 725 over 1 plus 8.295 e to the power 0. E to the power 0 is 1, so you get 725 over 1 plus 8.295, which is 725 over 9.295. Let's divide this thing. 725 is on the top, divide by 9.295. So rounding to the nearest whole number, it is going to be 78. So it's almost equal to 78. If I go back and try to understand the unit, it is in millions. So what I will say, that is the initial population of United States in 1900. T equal to 0 represents 1900s. So P0, so 78 millions, it said that interpret, so I will say that. Millions was the initial population. Of United States in 1900s. Use the function to predict US population on January 1, 2020, round to the nearest million. So I'm going to now use the same thing, but I want to do it in 2020. So 2020, I want to find the t. So in 2020, t is equal to 2020 minus 1900. That's where the census started. So I'm going to go ahead and set off 0 minus 0 is 0, 2 minus 0 is 2, 10 minus 9 is 1, 1 minus 1 is 0. So this is 120 years. So all you need to do in that PT equation, now you're going to put t equal to 120 and see what happens. So it is 725 over 1 plus 8.295 e to the power minus 0.0165 times 120. And I will do the rest of the calculation in my calculator and round to the nearest whole number. So let's see. We're going to first take care of the power. So I have 0.0165 times 120. So minus 0.0165 times 120. And I'm going to raise this thing to the power of e. So I'll go ahead and say e to the power, the answer. I get this number. Then I multiply 8.295 with that. So times 8.295. Then I add 1 with that, and this becomes the denominator. So what I do, on the top I have 725, so I say 725 divide by this newfound answer, and the answer is 337.95. So rounded to the nearest whole number, it's 338 million people. 338 million people in 2020, January 1. Use the function to predict US population in January 1, 2050. So in 2050, so it's pretty similar work, except in 2050, the t is going to be 2050 minus 1900, so 150 years. And I'm going to repeat the same work. So I will say P of 150 this time, T is 150, is 725 over 1 plus 8.925 e to the power minus 0.0165 times 150. And the rest is calculator and round to the nearest whole number. Let's see. So minus 0.0165 times 150 is in the power of e. So e to the power, I'm going to say the answer. which is this number. Then I'm going to multiply that by 8.295, just the way we have done last time. Add 1, and this is the denominator. So now 725 is the numerator. So I will divide 725 by the answer. The population is rounded to the nearest whole number, 427. So in 2050, the projected population is around 427 million people. What next? Determine the year which US population will reach 500 million. So this time, 500 million is the final population, and you want to solve for the t. So 725, and then you have 1 plus 8.295 e to the power minus 0.0165 t. So this one requires a little bit of work ahead. So what I will do, I will multiply the denominator on both sides for the same purpose, getting rid of the denominator. So 1 plus 8.295 e to the power minus 0.0165 t. Multiply it on the left and on the right. So 1 plus 8.295 e to the power minus 0.0165 t. What it does, cancels the factors. Then I will divide both sides by 500. So what I will get 1 plus 8.295 e to the power minus 0.0165 t is equal to 725 over 500. Subtract 1 from both sides, and I get 8.295 e to the power minus 0.0165 t is equal to, if you subtract, remember 1 is 500 over 500, so you get 225 over 500. And if you think of dividing both sides by 8.295, then you will get e to the power minus 0.0165 t is equal to 225 over 500 divided by 8.295. For simplicity of the problem, I want to simplify this number first and say round it to 4 decimal places on the right hand side. So I have 225 divided by 500, and then I'm going to divide it by 8.295 and round to 4 decimal places. So I get 0.0542. So I get, this is the right hand side. Left hand side is e to the power minus 0.0165 t. Remember, this is exponential equation, so you will take natural log on both sides. 0.0165 t is equal to natural log of 0.0542. So they will cancel, and you got negative 0.0165 t equal to natural log of 0.0542. Divide both sides by negative 0.0165. So now round your t to the nearest whole number. So this will imply that t is, I'm going to use the calculator, of course, to answer this question. T, and round it to the nearest whole number. So let's see how much we get. I have natural log of 0.0542. Natural log 0.0542. And then I'm going to divide this quantity by minus 0.01, round to the nearest whole number. So that will be 177. So it is around 177 years from the 1900s. So I will say in around 2077, the population will be around 500 millions. The next question is, what value will the term e to the power 8.295 over 0.0165 t approaches as t goes to infinity? So if you can think of, as t goes to infinity, the number 0.0165t. So as t goes to infinity, this number also goes to infinity. So I have a small number on the top, 8.295. I divide it by a large number, 0.0165t. So I say as t goes to infinity, this number will get smaller and smaller. You have a small number, you're dividing it by a large number, so this number is getting smaller and smaller. So I get to say, hence, as t goes to infinity, e to the power 8.295 over 0.0165t will go to e to the power 0, which is 1. So this number will approach 1. Okay, so we'll go ahead and answer further questions. The number of computers NT in millions affected by computer virus can be approximated by a formula n of t equal to 2.4 over 1 plus 15 times e to the power negative 0.72t, where t is the time of months after the virus first detected. Determine the number of computers initially affected when the virus was first detected. Remember, initial means your t is equal to 0. So you're finding n of 0. So that's 2.4 over 1 plus 15 times e to the power negative 0.72 times 0, because you're putting t equal to 0. So you get 2.4 over 1 plus 15 times e to the power 0. So it's 2.4 over 1 plus 15, which is 2.4 over 16. And this number is going to be approximately equal to, if I divide it by 8 on both top and bottom, I get 0.3 over 2, which is equal to 0.15. So 0.15 many computers doesn't make any sense. So I will say that approximately equal to 0 computers were affected before the virus was detected. Initially, there was no computer detected. How many computers are infected after 6 months? Round to the nearest 100,000. So now I'm going to use t equal to 6. So n of 6 is what I'm looking for. So I get 2.4 over 1 plus 15 e to the power negative 0.72 times 6. And as usual, as like in the last problem, we're going to try to answer this question by putting in the information in the calculator and round to the nearest whole number. Okay, so we're going to first talk about the data on the power. So minus 0.72 times 6, this is the power, raise it to the power e. So I will say e to the power answer. And then I'm going to add, multiply 15 with that and add 1. So times 15, add 1. This is the denominator and you are dividing 2.4. So you will say 2.4 divided by the answer. And I got, rounded to the nearest whole number, it will be 2. But remember the unit is hundred thousandths. So it will be 200 thousandths approximately equal to 1,000. Determine the amount of time required after initial detection for the virus to affect 1 million computers, round to 1 decimal place. So remember, 1 million computer is going to be how many zeros after 1? So you will have 1, 2, 3, that's 1,000, and this is going to be 10,000, and that's 100,000, and this is 1 million. So this is 100,000. So when I have 1,000, so basically your units are in hundreds of thousands. So I'm going to call it a 10,100,000. So I will say find the t when n of t is 10, because I want 10,100,000 to make it for 1 million. So as we have talked about, it's tens of hundreds of thousands. So 10 is equal to 2.4 over 1 plus 15 times e to the power negative 0.72. I was using negative 0.072. And t is what I'm going to try to find out. Okay, so as we did the cross multiplication, it is still going to be the same thing. You will get 1 plus 15 times e to the power minus 0.072t. Again, I said 0.072t. It should be 0.72t is equal to 2.4 over 10. So subtracting 1, I get 15 e to the power minus 0.72t is equal to 0.24 minus 1. So I get, dividing both sides by 15, e to the power minus 0.72t is equal to negative 0.76 over 15. Then I took the natural log on both sides. So you get natural log of e to the power 0.72t is equal to natural log of minus 0.76 over 15. So now at this point, what I want you to understand after I have done this much, look at the natural log quantity on the right hand side. This number, negative 0.76 over 15, is a negative number. Since this is a negative number, I cannot take the natural log of this negative number. What does that tell me? It tells me that the number of the affected computers cannot ever be a 1 million computers. So since natural log of negative 0.76 over 15 does not exist, I cannot take the natural log of a negative number. I will go ahead and say that the number of affected computers cannot be 1 million. And that would answer this question. What is the limiting value of the number of computers infected according to this model? So when the question asks what is the limiting value, what you are trying to understand is what if t goes to infinity? What happens when t goes to infinity? It's just like the last problem. So I say as t goes to infinity, think about the term e to the power minus 0.72t. What happens to this thing? Well, since t goes to infinity, 0.72t goes to infinity. So minus 0.72t goes to negative infinity. Think about the exponential function. This is the graph. As your t goes to negative infinity, e to the power, so since negative 0.72t goes to negative infinity, I get to say e to the power negative 0.72t will go to the height 0. It is approaching the height 0, and hence we're going to say that this portion over here is approaching 0. So I will say that the limiting value is p of t equal to, actually in this problem we used n of t, so we'll say that n of t is equal to 2.4 over 1 plus 15 times 0, which is equal to 2.4 over 1, and that's 2.4. Rounded to 2, so it will be 200,000 computers. So basically what it is talking about, when the number of infected computers reach 200,000, at that point this virus will be detected and eliminated, and that's what the limiting condition means for our problem. Okay, so we'll carry on and we will try to work out our next set of problems. Again, these are different application problems for exponential and logarithmic function, and this one is about a function of the form pt equal to a times b to the power t, representing the population of the given country t years after January 1, 2000. Write the equivalent function using the base e, that is, write a function of the form pt equal to p0 e to the power kt. Also, determine the population of each country for the year 2000. So since this study started in 2000, the initial population is t equal to 0. For Costa Rica, so what I do first, I put t equal to 0 in the given function. So I get 4.3 times 1.0135 to the power 0. So this is 4.3, and remember the units are given in millions. So that is for Costa Rica. And then the next one, so I'm going to go ahead and say that the population in 2000 is 4.3 millions. For Norway, I do the same thing. I find p of 0, and that is 4.6 times 1.0062 to the power 0, and that's going to be 4.6 millions. But remember, now we are supposed to find out the population with respect to the base e. How to do that work? So what we will do, we will find out p of 10 for both countries. So for Costa Rica, p of 10 using the old formula is going to give you 4.3 times 1.10135 whole to the power 10. Let's find this number in our calculator, and what we will do, we will round the answer to the nearest one decimal place. So I'm working on 1.0135, 1.0135, and I'm raising it to the power 10, and then this number I'm going to multiply by the initial population 4.3. So times 4.3, and that is rounded to one decimal place is 4.9. So what I have now, the population of Costa Rica in the year 2010. I will think of that as my final population, so 4.9, and I will say that this is equal to the initial population 4.3 times e to the power, remember your formula, k times t is 10, and that's an exponential equation, and we would like to solve this exponential equation. So it's standard process, you divide both sides by 4.3 and take natural log, and you get natural log of 4.9 over 4.3 equal to natural log of e to the power 10k is just 10k, and then I divide both sides by 10 to get k. So I get k is natural log of 4.9 over 4.3 over 10, and that is going to give me the rate of growth for Costa Rica in order to set up the model. And this time I'm going to round to 4 decimal places. So let's try to do that. I have 4.9, which I'm dividing by the initial population 4.3, and then I'm taking the natural log of that. Finally, I'm dividing it by 10, rounding to 4 decimal places. I get 0.0131. So k is approximately equal to 0.0131. That helps us set up the model. So what is going to be the model? The model for Costa Rica is going to be p of t equal to, remember this is 4.3, the initial population, times e to, I don't have enough space here, so let me write down beside this. So p of t is equal to 4.3 times e to the power 0.0131 times t. That's the population model for Costa Rica. Let's do the work for Norway now. Do the same thing, find P of 10 from the given equation. So you get 4.6 times 1.0062 whole to the power 10. So let's find this number in our calculator, and then we're going to round it to the nearest tenth. So this time you are taking 1.0062 and you are taking the 10th power of that, and finally you're going to multiply this by the initial population, which is 4.6. So times 4.6, round it to the nearest tenth, so 4.9. So I will be able to say that it is going to be 4.9 million. Pretty similar data for both of them. And then I would find the value of k the way we have found in the last one. So use 4.9 as the final population, 4.6 as the initial population, e to the power k times 10. Divide both sides by 4.6 and take the natural log. So you get natural log of 4.9 over 4.6 equal to 10k, just like the last one. So k is approximately equal to natural log of 4.9 over 4.6 all over 10, which will be done in calculator, and we will round to the nearest 4 decimal places. 4.9 divided by 4.6, take natural log of this answer, divide by 10, round to 4 decimal places, you get 0.0063. So this is approximately equal to 0.0063. So I get to say that for Norway, the population model is 4.6, that's the initial population, e to the power 0.0063t. That answers the first question. The second one is asking you, the population of the two given countries is very close for the year 2000, but their growth rates are different. Determine the year during which the population of each country will reach 5 million. So now I want to understand when those countries' population will be 5 million. So final population is 5 million. I will say 5 equal to 4.3 times e to the power 0.0063t, and this is for Norway, and then we will do it for Costa Rica. So again, I will divide both sides by 4.3, take natural log. So natural log of 5 over 4.3 is equal to natural log of e to the power 0.0063t. So divide both sides by 0.0063, you get natural log of 5 over 4.3 all over 0.0063 is equal to t. So let's find this number in our calculator. We're going to round it to the nearest whole number. That will be the number of years. 5 divided by 4. I think it should be 4.6 because I was doing it for, yes, I was doing it for Norway. Norway will be 4.6, so we should divide by 4.6. So I have to change some of these digits. So for example, this one, and this one. So let's write it down one more time. 5 is equal to 4.6 times e to the power 0.00. So divide both sides by 4.6. We get 5 over 4.6. We take the natural log. That should be equal to 0.0063t. Divide both sides by 0.633. So natural log of 5 over 4.6 all over 0.0063 is t. So let's do that in our calculator. Divide by 4.6, and then I take the natural log of this answer, and finally I divide it by the growth rate, which is 0.0063, and round to the nearest whole number. So that's around 13 years. So t is around 13 years from 2000. So we'll say that around 2013, Norway's population will be 5 million. Let's do the similar work for Costa Rica now. For Costa Rica, we will have the equation. So I want 5 million, but it started at 4.3 millions. And if I look at the population model, I will say this is e to the power 0.1 0.0131 t. And I do the same treatment. I divide both sides by 4.3, so I get 5 over 4.3. Then I take natural log, should be equal to 0.0131 t. Divide both sides by 0.0131, so you get natural log 5 over 4.3 all over 0.0131, which is approximately equal to t. So let's find this number in calculator, round to the nearest whole number, would answer my question. 5 divided by 4.3, take the natural log of this number, and then divide by 0.0131, that's the growth rate of Costa Rica, and round to the nearest whole number, so that will be around 12 years. So it's pretty close. So t is around 12 years, and what I get from this one is that around 2012 in Costa Rica, around 2012, the population will be 5 million. Answers my question. We have one more problem for exponential applications, exponential functions application. 2 million E. coli bacteria are present in a laboratory culture. An antibacterial agent is introduced and the population of bacteria PT decreases by half every 6 hours. So remember the half-life, it is 6 hours. The population can be represented by an exponential function PT equal to 20,100,000 times 1/2 to the power t over 6. Convert this to an exponential function using base E. So again, you just choose one t. So I find this value for two t's. Say for t equal to 0, that's my first target. So if I use t equal to 0, p of 0 is going to be, as I said, it is 20,100,000 times 1/2 to the power 0 over 6. So that's basically 0. 1/2 to the power 0 is 1. So this one is 20,100,000. So remember, this is your initial population. I can call it P0. Then let's find out P of 10. So actually, you know, I can actually try P of 6. That might be easier. And that will be equal to 20,100,000 times 1/2 to the power 6 over 6, because t is 6. So that's 1. So this is 10,100,000. So what does that tell me? If I presume that Pt is equal to P0 times e to the power kt is the decay equation, then final being 10,100,000 at time t equal to 6, and initial being 20,100,000 at t equal to 0, e to the power k times 6 will satisfy this equation, and then you solve for k. So I get 10,100,000 over 20,100,000 equal to e to the power 6k. I take natural log on both sides, as the number of zeros are same on both top and bottom. I get natural log of 1/2 is equal to natural log of e to the power 6k. Implies 6k is equal to natural log of 1/2. What does that mean? It means I can divide both sides by 6 and get k. So k is equal to natural log of 1/2 over 6. So let's find this number, round to 4 decimal places, and I get to write the decay equation. 1 divided by 2, take the natural log of this answer and divide it by 6, round to 4 decimal places. So that's negative 0.1155. So k is negative 0.1155. So the decay equation will be given by P of t equal to, remember P naught is 20,100,000 times e to the power minus 0.1155 t. So let me write it in the separate line so that we can understand and use it in future. So as I said, P of t is equal to 20, 100, 1000 e to the power negative 0.1155 t. That is the answer to the first question. The second one is asking me to find P of 6, P of 12, and P of 60. So first, it is asking me from part A, yield the same result for P of 0. So I'm going to find P of 0. So if I say P of 0, then I get 20, 100,000 times e to the power negative 0.0. Actually, this is 1155. So 1155 times 0. But doesn't matter. If you multiply 0, it is 0. So this is going to be 20, 100,000. So that number doesn't change. P of 6, remember, at 6, I'm going to put t equal to 6, so I will get 20, 100,000 e to the power minus 0.11556, and we will evaluate that in the calculator very soon. Then I will do P of 12. So now you are using t equal to 12, so you will get 20, 100,000 e to the power negative 0.1155 times 12. Finally, we do it for t equal to 60. So P of 60, we'll find this in calculator too. So 20, 100,000 times e to the power minus 0.1155 times 60. So let's find these three numbers in the calculator. And what we will do, we will round them to the nearest whole number. So we'll start with t equal to 6 first. It is minus 0.1155, that's the decay rate, times 6. And I take the exponential power of this number, so e to the power, the answer. And then I multiply this by 20, 100,000. So I get, rounded to the nearest whole number, 1000147. Approximately 1000147. Then I do it for 12. If my t is equal to 12, so you do minus 0.1155 times 12, and then you take e to the power, this answer power, and multiply by 20, 100,000, rounded to the nearest whole number. So that's 500,147. And finally, I do it for 60. So minus 0.1155 times 60 e to the power answer times 20, 100,000, and rounded to the nearest whole number, that's 1956. And that answers my question. This is kind of going to wrap up our discussion about the application problem for exponential and logarithmic function. I have done plenty of problems. Please go over and do your homeworks in Top Hat. If you have any further question, let me know. I will get back to you as soon as I can.